Okay. Now we are discussing about the color. See, we saw position, we saw the covariance, which is determining the shape, size, and the orientation. And we also saw the opacity, which is determining the transparency of 3D Gaussian. Now, one more very important parameter is the color. Now, while dealing with 3D Gaussian, we will not be using RGB color. Like, why RGB alone is not enough? So what's the problem that if we just use RGB, what challenges we will face? Let us see that. See the if we talk about the red, green, blue, the RGB assumptions and flaws. See, the idea is that if you use a simple RGB, then what will happen is that from all the directions it will look same. So simple RGB, it assumes that a point has the same color from all the viewing angles, like constant color. So simple RGB, it assumes the color to be constant. Color to be constant means for a pixel, whatever the color, it has to be same if we look it from any angle. But we know that in real world, it does not like that. It is not like that, because in real world, we have glossy surfaces like specular highlights, reflections, Fresnel effects, and glossy materials. And in real world, for a same point, if we look it from different angles, the color it changes. So that's why RGB is not a good choice to represent colors of a 3D Gaussian, because 3D Gaussian, it will represent a real scene. And since it will represent a real scene, it has to take care of the lighting conditions. And the solution for that is direction dependent color. The solution for that is direction dependent color. So direction dependent color means now the color will no longer be constant, rather color will depend on the view direction. The color will depend on the view direction. The color will be the function of the view direction. So if we look it from a direction, its value will be something else. If we look it from any other direction, its value will be something else. So if we talk about an example, if we talk about a shiny car, it looks bright from one angle and it looks dark from another angle. So the same point from different angles, it's like a function of the direction. And that is called as direction dependent color. Now, how we will get direction dependent color? So for that, we will be using something called as spherical harmonics. So in order to represent color in a 3D Gaussian, so the color of a 3D Gaussian is represented using spherical harmonics. So basically spherical harmonics, they are functions defined on a sphere that can represent directional signals. So see, basically spherical harmonics, what they are functions defined on a sphere and they represent directional signals. So basically spherical harmonics, it is like a mathematical technique. It's like a mathematical function which is defined on a sphere. And why sphere? Because sphere, it takes care of all the directions, all the angles. Because if I talk about sphere, all possible angles it is covering. So spherical harmonic is like a mathematical function which is defined on a sphere. And since it is defined on a sphere, it can take care of all the directions and hence it represents directional signals. So spherical harmonics, it is mathematically, it's a mathematical function which is representing all the directional signals. It is containing all the directional signals because it is defined on a sphere. It considered all the possible angles and we will make use of it to define the color of a 3D Gaussian. Now let us understand this formula. Now see, CD is the direction dependent color and D is the direction. Now it is like the double summation. Now what this double summation and all that we will understand very soon. But and this we have something like K, LM and Y, LMD. Okay, so let us try to decode it, how it works. Now see, D is the viewing direction. Now it can be any direction. So D is like a variable in this formula, wherein D can take any value. It is representing the direction. And this formula, what it should do is that for a particular direction, it will give us a value, and that value will be the color for that direction. That is the significance of this formula. Like this formula will take a direction, and the result of this formula, the output of this formula will be the color for that direction. So we will get the direction dependent color. Now how this formula is working? So this formula is making use of YLM. Y and LM is in the subscript. So this Y is like the spherical harmonic basis. Now here see L and M is used. So L is the degree and M is the order. So two things are there, degree and order. Now degree means like we can have 0 degree, 1 degree, 2 degree, 3 degree. So this degree, it controls the, or it decides the realism. Like let us suppose if we don't want like detail, if we don't want like very high realistic scenario, we can choose low degree. Like we can go with 1 degree. So in order to understand this properly, you should refer this table. Now see here, if the degree is 0 degree means constant color, no variation at all. 0 degree means constant color. So if the degree is 0, there will be only one coefficient and constant color. If degree is 1, then we will be having four coefficients that will decide the color. So we will have something called as diffuse shading because of these four coefficients. If the degree is 2, then we will have 9 coefficients. So the color will be more realistic. Specular hints the quality will be. And if the degree is 3, coefficients will be 16. So very high photorealistic experiences we will get. So that is how the degree is deciding the quality of the color. So if we go for higher degrees, it will be more precise, it will be more photorealistic. So most 3D Gaussian implementations, they use order 2 or 3 because it balances realism, speed and memory. So that's the idea. So here small l is taking care of that degree. So let us suppose if we are going with the 3 degree, then the outer summation will be 3 times. Like L is equal to 0, then L is equal to 1, then L is equal to 2, then L is equal to 3, rather 4 times. If we are going for a degree of 2, then 0, 1, 2, 3 times. And the inner summation, the small m, it is the coefficient, because we know that if the degree is 2, the coefficient will be 9. So it will go 9 times, like for every coefficient. And this KLM is the learned coefficients. Okay, so here m will be from minus small l to capital L. Okay, so m is not the number of coefficient, rather this k will be the number of coefficient. So I'll tell you an idea of what is happening. See, the idea is that let us suppose we fix 1 as the degree for understanding purposes. So when 1 is the degree, the capital L will be 1. So the outer summation, it will be 2 times, like for 0 and for 1. For 0, it will be from 0 to 0. The inner summation will be only 1 time. And what it will do is that when the degree is 1, we will have 4 coefficient. So here 4 products we will add. Like for first coefficient, the spherical harmonic basis, that we will get from this spherical harmonics. That I'll add with the second coefficient multiplied by its spherical harmonic basis. Then the third coefficient and the fourth coefficient. So this we did. Like first coefficient multiplied by spherical harmonic basis, plus second coefficient, third coefficient, fourth coefficient. Then outer summation, it will become 1. So when it will become 1, like a small l will become 1, m will be from -1 to 1. So now it will be 3 times. Like for -1, it will be, then for 0, then 1. And that's sum we will do. And finally, we add all this. And we will get the color, direction dependent color. Now, what exactly is this and how this is been taken care of, that we will not discuss now. But you got an idea how it is working. So now it's very clear that if we talk about 3D Gaussians, they make use of spherical harmonics, that is a direction dependent color. And spherical harmonics, it is basically a mathematical function defined on a sphere, and hence it is representing the directional signals. Now we have degree. Degree will decide the quality, and based on the degree we will having coefficients. And this formula which we saw, it is taking care, it will give us the direction dependent color. If we talk about why simple harmonics works well, because it takes into consideration smooth angular variation, efficient evaluation. Because a smooth angular variation, it is taking care of, because spherical harmonics, all the directions we can consider. And efficient evaluation, it is differentiable, that is very important. Since it is differentiable, we can optimize it, and it is compact representation. So visual intuition, if we talk about spherical harmonic, it acts like a set of soft lightning lobes around the Gaussian that change brightness depending on camera angle. So spherical harmonics, the beauty of it is that when you change the camera angle, automatically the Gaussian, its color will change. Color means its brightness and the lightning conditions, it will change, and color will also change accordingly, the shininess and all that. And that makes sense also. That makes sense also. Okay, so now it's very clear that if we talk about a 3D Gaussian, each Gaussian, it will store the position, the shape, and here the shape, size, and orientation will be taken care by the covariance matrix, the opacity, and for color, it will be making use of SH, like the spherical harmonic color coefficients. Because here, this color coefficients, we will learn it, we'll optimize it, and the learned color coefficient, it will be important, because see, spherical harmonic basis will be same. Like for different directions, it will be a fixed number. But this color coefficient, we have to learn it. So this learned color coefficient. So now the idea is very clear. For 3D Gaussian, for a single 3D Gaussian, we will learn the position, the mu. We will optimize the covariance matrix, wherein we will be having covariance matrix containing information about the shape, size, and orientation. We will learn the opacity alpha, and we will be, for color, we will be learning the SH color coefficients. And the number of coefficients will depend on the degree which we are considering. So it can range from 1 to 16, the number of coefficients. So for 0 degree, the number of coefficient will be 1. For 1 degree, it will be 4. For 2, the number of coefficient will be 9. And for 3 degree, the number of coefficients will be 16. And see, if we store color per angle, that can be very messy. The storage will be huge. And rather than storing color per angle, we just now need to store the SH coefficients. So if the degree is 2, 9 coefficients I have to store. That's it. And that 9 coefficients will be enough to determine the lightning or the color of a 3D Gaussian. So every Gaussian will be storing 9 coefficients for color.